All right, well, thanks very much, everybody, for coming. We're going to continue with the talk we did last year, where we started to look at the journey of a raindrop on the island. And we thought it was probably the best way of describing what we're doing and how the information we're collecting to understand the cloud forest function for water supply works within the physical environment of the island. So we're going to take you through that over the next few, tens of minutes. I'll first of all just say, though, that while we talk to you about what we've been doing, there are a number of things that we've done on the island on this project that haven't been done before from a geological, water resource and climate perspective. So we've been using geophysics for the first time to actually understand a little bit more about what's going on beneath our feet. We've had some boreholes drilled in the past, and we have some information from those that people may know about. Geophysics is a less intrusive way of beginning to collate information on the subsurface. Robert and Michel will take you through that process later on during the presentation. We also have been using a borehole camera, and that's been very useful to understand the condition of some of the deeper boreholes in the island and help us understand a little bit more about the geology, where we can get information from those about the bedrock. Murray's going to take you through the climate data we've been collecting, how we collect it. And one of the fantastic things on this project is, for the first time, we've actually been able to telemeter environmental data back to the office, to Bottomwoods Met Station, and actually be able to use that data and see it in real time, which is incredible. And we've also been using some slightly different water quality analytical techniques. We've been using stable isotope analysis, which we've been reporting on as well. And Murray circulates data around to all the project partners and other interested parties on the island on a monthly basis. So we're already seeing that data is being used on other projects that are being delivered on the island. So what we'll do, this is a lovely basic schematic on the water cycle, but we will take you through the climate to the cloud forest, and then we'll look at the journey of the kind of data we're collecting to look at the groundwater and surface water and the flows, and then on how we're understanding how the geology fits in with the water resources of the island. Okay, so I'll hand over to Murray now, and he'll take you through the climate monitoring stage of the project.
Okay. All right, thanks, Ben. Thank you all for coming. So I'm just going to talk about the climate monitoring and some of the equipment that we use for monitoring of our weather data. So this is a picture of just us setting up some of the stations. So the one on the left is Southwest Point, and the one here is at Flagstaff. I'm not too sure if a few of you might have seen a couple of these around the island in your travels. But just to give you a breakdown of what they actually incorporate. So number one, which I have a model here. So this is the Davis Vantage Pro AWS, so automatic weather station. So this is basically the main component of the weather station. So within here, you have a temperature sensor, your rain gauge, and then you also have a anemometer, which is attached on the back, as you can see in the picture. And all those sensors feed into the main board. So this is the transmitter board. So they all plug and play into the various ports. And these actually transmit the data wirelessly to a console. So the console, which I can show you as well. Looks like this. So this is basically a console. So it just takes all the information from all the sensors and displays it in one easy to read format. In addition to this, though, we have a Wi-Fi logger, which is situated in the back of the, if I can get it in. So this little device here is basically the Wi-Fi logger. So this is allow us to actually transmit the data that it collected into our various data portals, and then we can access it remotely. So it goes from number one, which is the sensor suite. The basic three sensors, as I mentioned, is temperature, rain, and wind. All that gets transmitted wirelessly to number three, which is the solar power shelters. So one shelter just has batteries that allows it to work offline, so completely remote, no power, no external power needed. And then in the next one, we have the console, just to protect it from the weather and to make sure it functions correctly. And then number two isn't part of the actual AWS system. That is actually an addition that we kind of added ourselves. So it was a trial and error at first, because we anticipated that it should work, but was kind of took the gamble and decided that we was going to test it just to see if it would work. So that is actually a Wi-Fi router. So all it does is basically it takes you shore mobile SIM and allows you to connect to it via Wi-Fi, which the Wi-Fi logger in here allows us to do. And then it transmits to that Wi-Fi router, and then it transmits that into the internet, into our various portals that we set up. And then number 4 is basically just the solar panel that we use to help power the Wi-Fi router. It has solar power batteries in it as well, but it does also need the panel just to kind of keep the charge up. And out of all the AWSs that we have, this is basically a map showing the layout of the AWSs around the island. So Flagstaff, Jamestown, Persistence Walk, Horse Pasture, Southwest Point, Buckswood, and the peaks, High Peak and the depot. High Peak, the depot, and the peaks, those are the main 3 for the Cloud Frost project, whereas the others was installed through our Darwin Plus project, which is now concluded. And then we also have the Met Office. So all these stations feed straight back to the Met Office, so we don't have to physically go out on site and download data every month or so. We can get it pretty much in real time. So this is a few climate graphs that we created from our 2022 data. So you can see various patterns in it. Flagstaff has some gaps between February, March, and June. That's because we had some technical issues with that one. So we had to get a few parts in, but we managed to get it back up and running again. And then we also have Horse Pasture, Southwest Point, and High Peak. You can kind of notice a similar trend, whereby the temperatures are pretty high from January, from December really to March, and then as we go into our more wetter and colder months, the temperature decreases. And with that, the rain increases. So you can kind of see that similar trend throughout all the various stations. Can anybody guess which one had the highest temperature? Yes, Sisters Walk. Yeah, so Sisters Walk had the highest temperature. I think I have it in a summary here of what it was. So yeah, this is basically saying what I mentioned before about you can't really tell the seasons between spring and summer, and autumn and winter here. You can tell when it's summer and when it's winter. But you can see from the information that they pick up that there's some slight changes. So as you can see, the temperature starts to decrease from March as we start to move into our autumn and winter, and then increase again from September as we go into our summer, spring period. Rainfall is higher within our winter months than for our summer. And yeah, so Sisters Walk was the highest temperature, so that had a 31.4 degrees in February, whereas Horse Pasture had only 10.7, and that was recorded in August, which is usually our last month for our winter period. And the location with the highest rainfall was High Peak. That area is usually pretty wet, so it's understandable why we had 211.8 mils for April. And Sisters Walk, as people in town will know, we don't get a lot of rain in town, even during the winter months. But the lowest was 0.6, and that was for October. So going back to the telemetry information. So we have our AWS. For some reason, my S is missing. My apologies for that. So it's automatic weather. It's not a station, isn't it? So it goes from there. And then we have various portals which we have set up that will actually collect the data. So we have WeatherLink. WeatherLink is a subscription service that we pay for. And what it does, it basically collates all the information on a half-an-hour basis. So every half an hour, information is transmitted from all our AWSs to that web portal, and we can monitor it in real time. It's a really good data portal actually, because you can download any information you want from various periods, and also it does a monthly summary for you as well. So this is pretty much where I get the information from to do the summary for all the other local parties like National Trust or Connect when I send them data. Unfortunately, it isn't available to everyone. It's you have to have an account with them to be able to view the data. But like I say, hopefully we're going to look at WOW, which is another portal that we feed into, which is actually developed by the UK Met Office. So WOW stands for Weather Observation Website. This one is available for anybody to go on. You don't have to be a member or anything. You don't have to pay a subscription. They allow anyone to feed information to. So a lot of the UK small hobbyists, they can feed into the website as well. So we have all our stations incorporated into there. It's not as user-friendly as WeatherLink, but the information is there. But I do believe that they are looking to revamp that website at some point, and hopefully they will try to incorporate some of the features that WeatherLink has in it to make it more user-friendly. Another route we're going down is with ClimSoft. So ClimSoft is an open source weather database. I think it's mostly developed in South Africa. So I think countries like Nairobi, I think, has it. Might be Kenya, because they don't have a dedicated Met Office. They kind of have small offices throughout each region. So they have actually incorporated ClimSoft as their main database for collecting all their weather data. So this was recommended to us by Steve Palmer, who used to work for the UK Met Office. He led a few projects in Africa to actually get this started. So we want to try get it developed here as well. It has quite a few features. It has real-time AWS data. So it's whenever, I think it's every hour, you can get data from the AWS uploaded to that website automatically, and it will filter through, import it into the database, do the checks and everything so that it's live. It's quite straightforward to use. There's quite a lot of support for it. Being open source, you get a lot of various parties feeding into it, which is helpful. And at the moment it's free, so which I think will always be free. But we want to look at developing the information in that more, so that hopefully we can use that as our main platform, and then we won't have to pay for the subscriptions in WeatherLink. So we kind of save some money there. And then another way is through FTP hosting. So down there is just basically a screenshot of our NAS device we have at the office. So I have all folders for each the locations, and in there is actually a text document showing all the temperature, all the readings, so temperature, wind speed, wind direction, and a lot of other information. And then we can use that after to either feed into ClimSoft, or we can just view it ourselves. It's just as a check. There are so many other portals you can upload to. The Wi-Fi logger in there is pretty unique, whereby you can upload it to Wander Underground if you want, and there's quite a few other various exports you can do. So that's kind of the main brains of the whole AWS. Without that Wi-Fi logger in here, we wouldn't be able to have the telemetry set up like we do. Down below there is just the link for the Met Office website, where anybody can actually go on and have a look at the data if they want. And we do have a demonstration of that. So you just open up your usual browser. Whether you use Firefox, Chrome, it usually works with any browser. And then once you type in the URL, so metoffice.gov.uk, it should be faster now with our internet. So you'll get this page come up. So like I say, it's mostly for the UK, but you can either use the map to pan to it, or you can actually just search St Helena in the search bar. Once you do that, hopefully you'll know where St Helena is. Yes, it does. So you'll see an overview of the weather station. So this shows the weather stations that has been transmitted data, within the last hour. So Flagstaff is on there at the moment. Yes, because I have it here. It's down at the moment. I'm waiting for some speeds, unfortunately, but we have all the other stations running. So if you click on one, for example, Jamestown, it just gives you a brief summary of the current readings there for that particular hour of data they had. So it gives you the basic information that you're looking for, temperature, wind speed, rainfall, and pressure. But you can also look at full observations, where will give you some more detailed information about it. So again, you have a dashboard which gives you the basic summary of information. We have a little map to show you where it is, and we also have some site photos that is attached as well. And there is some details that we have to put in for the site to allow it to get it, so as you can see, it's like a bronze of wood. So the better your site is to be in terms of the data that's collecting, the higher the wood will be. So if you get a gold standard site, that's, you pretty much got the perfect site. Or this is bronze, because we don't have certain sensors that the other stations have. Then once you get here, you can actually look for detailed information. So you can go by filtering. You can filter the information whichever you want. If you want a specific attribute that you want to look at, for example, rainfall. And then once you choose your time period for when you want it, so for this one we went for the 1st of July, and you can update your graph. So it will show you rainfall from the 1st of July through to the 26th of October. And hopefully the graph should update. Must be a slow internet day when we did this. Here we go. So you see here we have information in there. There was a couple of gaps because Sisters Walk was another station that we had a few problems with, but we managed to rectify it after. But it will show you all the information there about the rainfall. Yes, and that is it for me. I shall now hand back over to Ben to continue.
Thank you very much, Murray. That's brilliant. And yeah, as Murray's shown you, feel free when you get home to have a look. It's really interesting just to see the work the Met team have been doing on the portal, and it's great you can actually get to see some of the island's data in your own home. It's great. So I want to take you then through some of the catchment monitoring work we've been doing and how that fits in with doing the water balance, because one of the things that we're working on for the Cloud Forest project is to establish the function of the cloud forest for providing additional water for the island's water supply. So as Murray's taken us through main climate data, we are also collecting mist data in many of the locations Murray's shown you and up in the peaks, and that's being added into the direct rainfall data so we can understand when we're collecting mist, how many days that might be, whether we have some mist days versus rainfall days. And then what we're working on at the minute is to understand actually how much of the mist we get up in the peaks is actually going to get into our water supply and help augment the amount of water we get from direct rainfall. So that's still a work in progress for us to do. With the catchment monitoring though, we've been collecting multi-year data now from several streams and springs and boreholes around the island, and we're linking that back in with the automatic weather station data so we can compare water levels and flows with rainfall events. So we can actually see how quickly it takes a catchment to respond to a rainfall event, and also just when we have longer drier periods, to see actually how long that particular source keeps flowing and how it maybe slows down over time. As I said, we're then looking at that data and comparing it to the geology of the area. We're looking at the vegetation, the topography and things to better understand when it rains and the water gets into the cloud forest, percolates down into the soil, how much of it is running directly off into the streams, how much of it's evaporating, how much of it might actually go down and percolate down into the soils and then eventually find its way into the aquifers. And over time, we hope that the data set will get bigger, it will get more robust, we'll have more confidence in the information we have, and that can be used to help the island support water resource management planning. So this is just a summary table of some of the data we've been collecting in Wellsgut and Legsgut. And we're gradually building some more confidence up with the data we're getting here, but we can calculate the amount of water that's flowing down various parts of the catchment there. On the very right hand side, we've actually compared it to data that was reported in the 1990 to 2010 water resource plan. And we're quite happy with the numbers that we're getting from that at the moment. And then this is just an example of the kind of chart we're producing where we're comparing water levels against rainfall. And over time, we will be looking at, as I said, the lag time or response time for the catchment. So when it rains and we have a high rainfall event, how quickly does it take different parts of the catchment to respond for water levels to increase? And then we've been doing the same for some of the boreholes on the islands as well. This is an example of some of the boreholes at French's Gut, and we've overlain the seasonal groundwater level data over several months with the rainfall events. And again, we're looking at that to see how the groundwater levels might respond to rainfall events over time. And then, as has been done in the past, we're actually looking at creating a more robust water balance to understand how much water do we actually have, potentially, in the system. So we're collating all the information that we know about the catchments, and we'll hopefully use that data to provide a more robust forecast on the kind of water resources and supplies we might have, and then we can make better decisions on how to manage that water supply. And another part of the project we're doing is, over the next 6 months, is working with the UK Centre for Ecology and Hydrology and actually developing some climate scenarios where we can actually then add those into the water balance and stress test the system and understand, what likely impact would be on climate change on our rainfall, the frequency of high intensity rainfall events, of dry periods, and then we can begin to see how much of an impact that might have on our predicted water balance. I'm going to just give you an example of how the approach that we're using on the water balance. So I've overlain this picture with the water catchments for the island. What we've done is, instead of looking at an average rainfall for the whole of the island, this time round we're using the more detailed information we've got from the rain gauges on the island, but now all the automatic weather station data. And we've split the island into three zones. So we've taken all the land above 690 metres elevation, which is the area of the island that we believe could have some contribution from mist to support recharge. So that's where we're looking at mist and rain. And then we've got the area between 500 metres and 690 metres elevation, where we believe it's just rainfall that would be the main contributor to groundwater recharge and stream flow. And then we've got the remainder of the island below 500 metres. And going back through all the previous reports that have been done in the past on the island's water resources, evapotranspiration, evaporation tend to exceed any rainfall recharge for the whole year, so you're unlikely to get any contribution, certainly to groundwater resources and stuff below that elevation. What that means is, for each catchment, we've actually got 3 different values for rainfall recharge, so we can hopefully develop a little bit more of a detailed water balance to see how the different catchments are responding at each of those different zones. And we're folding back into that all of the stream flow and the groundwater data we've got to see how the water balance could be impacted by these differences. And then on top of all that, as I said, we've been, this slide really just highlights the rainfall data that we've used that Murray's collected. Murray's put it into the GIS for us, and we've been using that to work out how much rain we're likely to get in each of those zones in each of the catchments. And this is just an early doors example of the kind of work we're doing on the water balance. So I've got just 3 different versions of the water balance that we've been looking at. The one is just assuming an average rainfall for the whole of the island, and assuming all the mist might be available for recharge, which is our kind of, it's an unrealistic target, but it just allows us to look at ranges. Then what we're looking at is, the second run is just looking at the rainfall that we've actually monitored in each of those zones I've described, and then looking at the total mist. And now the mist would only be included for the top zone, the 690 metre and above elevation. And then the third one I've got there is assuming we've got the rainfall for each of the zones, but we're only looking at 10% of the mist being available for groundwater recharge and for stream flow. And what we're going to do over the next few months is run a number of different scenarios as we get the data processed and refined. But just as a comparison, when you look at the total island discharge that we've got for the 3 scenarios there, we're ranging between 2.55 million metres cubed per annum to 6.63 million cubic metres. And if you look at the three different sets of historic water balances we've got, we are within an order of magnitude and within that kind of range of those previous balances. So the difference between the previous balances and what we're doing now is really just to try and look in a bit more detail about how each catchment responds. Okay. So that's me finished on the water balance for the moment. We will be getting all this work finished by the end of March next year, so we'll have a much more accurate and detailed assessment available at that point. But I'm going to hand over to Elizabeth now, and she's going to talk us through the island's geology. Thank you.
Thanks, man. So we've talked about the climate scenario, and also talked about our target, which is to look at how water responds on the island and what resources you have available. So what I want to talk about now is how does it get there, and how do we do the assessments in the field to provide information to augment and underpin the work of that contributes to the water balance. So with hydrogeology, the first thing you need to think about is the geology. And St Helena is gifted in having geology that's accessible, and that's really important for people like me, because you can go to places and you think you have a perfect site, only for it to be covered in concrete or in somebody's house. So, of course, everybody knows this. This is down at Sandy Bay, but Sandy Bay was a wonderful playground for us to actually understand a lot of aspects about the geology of St Helena, but also to help us to understand how the water does get into the aquifers and what the aquifers behave, how they behave, and how water moves through the island. So just a few things to think about as we go through. So local geology, especially in island states, it dictates the nature and accessibility of water resources on the island. Oceanic islands like St Helena have very complex geology, and following on from that, complex hydrogeology. Also important to note, the periods of activity of extrusion, intrusion, and weathering and erosion impose a specific signature in terms of how water performs in terms of surface runoff, springs, and groundwater resources. The energy throughout that process also releases, ash and pyroclastic deposits. The degree of weathering and erosion during these periods in between, because these are over millions of years. And the period of quietness, and in St Helena you had 3.5 million years break, and then another 3.5 million years of activity, volcanic activities. The period in between is really important for us to understand. So looking at the degree of weathering and erosion of those rock types by water resources, so it will cut down and create valleys. But then what happens, after that when you have another event? And understanding this and actually going in the field and looking for those signatures are important to help us to understand how the water moves through the various units, and what we see manifested not just in terms of quantity of water and accessibility, and it's also the quality of water. So the rocks that are eroded and will fill in valleys or foam valleys, the next event when you have the lava flow, and we have a wonderful example of that on the table, it then bakes those rocks. So you have that dehydration and weathering with the capping of that. So all of these dynamics in terms of the geology are important for us to help understand how that rock will then allow water to pass through it or not. So dikes in particular, which again, using the Sandy Bay example because it's spectacular there, but they can also block flow. So when we look at our sections and we, one well will perform spectacularly well, and another well very close to it, there is no performance, in other words, no yield. These are things that we look for. Do you have a dike there, and is that preventing flow? So an example. This is just another side of Flagstaff, where you can see the dikes perfectly, and they hold the topography in shape, so you can actually see the form. You have volcanic flows, which are nice layer cakes. And also you have the dark basalt flows, which are very dense, and the water moves through basaltic flows through fractures, because it cools, and we have an example of that over there in hexagonal formats. Sometimes because of the activity, you have a lot of fractures and fissures, and those create preferential pathways for water to move through the system and then become accessible. You also have, during those events, what we call hydrothermal fluids. Now, those will come with minerals that have dissolved in it, because it's really, really hot water, and then they precipitate out. And they are sometimes found alongside, these massive flows, or along with the dikes. And we have examples of gypsum, which you have, again, in perfect form on St Helena, and also zeolite. And, both are present, easy to access. But they themselves give us an understanding of the dynamics and activities, but more importantly, a signature of water quality. Because gypsum, as my colleague Michel will tell you, you put it in water and dissolve it and try and drink that. It's very bitter. So the chemistry of those crystals and minerals do give us an idea and appreciation of what to expect in terms of water quality. Here we have a spectacular example of what we call the sequence of events in a volcanic eruption. So you see at the bottom you have a pyroclastic flow, and that's all the debris. So the vent will be clogged, it will explode, and you've got very coarse particles underneath. But during that process you can also have what we call the volcanic bombs. So you have pieces of lava going up and it's spinning in there, so it forms almost like a cannonball. And in this example, it's falling back to the ground, and then it's covered by the ash. And those layers are not instantaneous. Those are, several millions of years, but it's there. And you have the next sequence of events above, which is another pyroclastic flow. And you have this in repetition. But why is that important? Because understanding these events helps us to understand what we see under the ground, because this is accessible, but we need to understand what is below surface, because then we need to then determine where the water is flowing, where the water is being held, and how then to access it and manage the water resource. So the geology dictates the form and shape. And as you can see here, you've got a beautiful example of where you will find good surface water running down, and areas that you have probably poor yield from that, as you can see there. So another aspect that we found when we're in the field, which hasn't been studied for St Helena, is faults. So this tube-like structure in the middle is actually a fault. So if you think of it being broken, and one part is turned up like that, the debris from that process forms this like a slug in the middle. But it's an indication that you have a fault line. And what we observed looking down, you saw richness of trees and the marsh grass, which indicates that you may have water in that area. So St Helena is not alone. These are all the ocean islands in the world, and they are going through the same issues as you have here, looking at water resources and how best to manage the water resources. So I'm just giving a couple of examples of that. So here we have Madeira, and the background looks very familiar, and because it's very similar to St Helena. So they are younger, the island's younger, and so their last eruption was 25,000 years ago. So quite recent in geological time. So, but the important thing to pull out of this is that exactly what Ben was talking about earlier about managing water and getting the water balance, they go through the same issues. And the rocks perform in a very similar way, but being younger, and the feedback from that is that we look at how these rocks perform, look at how the water is accessible, what yield we get from it, and learn from that for St Helena. Another example is Tenerife. As you can see, the vegetation is very similar, but if you notice the highest point is over 3,000 meters because it's still active. So you can see the Tene in the background. It's a lovely point to begin. That's probably what St Helena looked like, because you're looking at a severely eroded surface where we are now. So again, very similar, learning from the geology and the hydrogeology in other oceanic islands enables us to then look at the geology and hydrogeology in St Helena in a more informed way. So, the things that we focus on. So, the geology, the episodes are very similar, and they shape and influence the water resources. The quiet periods, erosion takes place. That's also very important for us because that provides, at times, good aquifers. And as I mentioned before, the later events then can bake those surfaces like a nice cake. But the material underneath, which is then baked, can provide a good sort of ground or aquifer for water to flow in and stay. So we also know that preferential pathways for movement of water can be created from fractures and fissures from the dynamics of the events that have taken place. And they enable water moving from in between geological layers. And there are some challenges because you can have water losses where the waters move through these fractures, or are impeded by dikes, as we've spoken about before. But more importantly, when we're looking and calculating, as Ben was talking about in terms of the water balance, sometimes you have a large missing factor, and that could be due to losses to the ocean. So I'm going to hand over now to my colleague, Michel. But this is just a summary of the geology of St Helena, and you are already familiar with the two volcanoes, one in the northeast and the other to the south. But Michel is going to take us through how the geology and knowledge of the geology enables the information that we gather from the geophysics to then inform, the whole concept of water resources. So, Michel?
Yes.
Yeah. Oh, and by the way, the rocks are there, so you can look at it later. But they're quite heavy, so I think, there you go.
Good. Well, thank you for coming here. I will tell you something about the geology and also related to the geophysical research we did in order to see not only the surface but also underneath the surface. This is a geological map, and when you see such a map for the first time, you think, oh, that's nice. Yeah, okay, nice colors. Put them above my bed, and yeah, it can be also in a museum. Well, this is a museum, but it gives you information. There are, what Elizabeth said, there are several. Here's the old volcano, here's the new volcano, and here we see actually series of the oldest part of the new volcano. And how can you translate this in a more vertical mirror? And actually this is what such a map shows. So this is just a schematic cross-section along the island, and this part is this color and this part is the gray color. And what happened here, this is actually Sandy Bay, and in Sandy Bay you see the oldest part of the volcanics. It's the lowest shield volcanics, and this is actually the middle shield, and just this small part is the upper shield. And the center, what you can also learn from this map, is that the center of the outflow was somewhere here. So this is all gone away by a huge landslide. So when you look at the map and take the topography and you make such a diagram, you can learn where you can expect which layer. And then when you see all sediments, river incisions, also dikes and fractures, you can understand that the hydrology and where the water goes is quite a difficult thing to find. So therefore you need, and that's also when you, well, geophysics is part of it, you need every information, every bit of information in order to understand what's happening. First of all, of course, the water balance. You want to know in a certain catchment if the amount of water that's coming in is also coming out. When not that amount of water is coming out, it goes to the ocean. And then we want to know, how does this go to the ocean? So you go to all the places where you can find information, like boreholes. This is the funny borehole of Ladies' Bath. Well, the ladies cannot take a bath anymore after they drilled this borehole. And we try to find, actually, yeah, that's true. With the camera we could see where the water comes from, at what depth. And we could close it with some sort of a packer in order to see whether the water will rise and it will flow again. But it doesn't happen because the filter, also outside the filter there was a hollow space. So the water is just disappearing down also through the filter and the hollow space down. So in order to restore this Ladies' Bath, you should just take out the filter and grout it up to the location where we find with the camera the inflow. And then probably Ladies' Bath will flow again. But according to the chemistry, Ladies' Bath has a lot of lead. So I wouldn't say go there just and drink it. And the lead is coming from, yeah, the graves upper from the St. Paul's Cathedral, where you have those huge lead sarcophages where they put the bodies in, and that lead is coming with the water that infiltrates there, and it goes also passes this borehole, and eventually it goes to Ladies' Bath. So when Ladies' Bath is restored, you can take a bath, but don't drink it. And then what we also see in the field is that that the surface of the top surface will be sealed. When the weathering, volcanic material weathers very fast, so a little bit of rain and rainfall and also air and humid from the air will seal the complete landscape with a sort of clay. So at those locations, water cannot infiltrate. So also what Elizabeth was explaining, in the older times you have those sealed landscapes and then new events passes. So you have layers of sealed, weathered volcanics, and then new volcanics, and then maybe fresh bedrock, and then again period of no flow, and then again we're the sealing, and also sealing by ash. So there's a lot of going on. The ash layers, that is also impermeable, so they also seal the aquifers. And but we also saw that that's also named by Elizabeth, that the dikes are also impermeable, some of the dikes. And you can see that at Ladies Pond. Lot's Pond, sorry. Lot's Pond. You can see that there's water above the ocean level. And it's the ocean just plunge it in and then it seeps out. So you can see when you look there, and you should go and look there, you see the dikes around it, and these dikes just keep the water in. And slowly the water goes out. So this is a proof that the water is kept within the dikes. So when there is a dike and the groundwater infiltrates, it will block like an underground dam, it will block the water flow. So all these things, they are important. And like here, and we will come back to this is a thermal infrared picture of from a satellite, and you can see with thermal infrared, a satellite can see the temperature of the seawater. And the temperature of the seawater is higher than the temperature of the groundwater. So when you see a black spot here, which you can see when you look very, very good, because the difference in temperature is not that big, then you find evidence that groundwater flows into the ocean. So all these things we come together, like here, you can see all the river courses at one side of the island: Young's Valley, Breakneck Valley, James Valley, Sarah's Valley, Svenley's Valley, Thomas Valley, Lemons Valley, Old Woman's Valley, all those valleys. And you see that they have a change in the topography at the same level. And you can also see that the springs are above this. So you could think that this zone is where the water infiltrates and disappears. Only at James Valley we see springs at a lower level, and that's because at James Valley you have the interface of the northwestern volcano and the fresher the northeastern volcano and the southwestern volcano. So when you do geophysics and when you do hydrogeology, you should all combine this information. All information is needed. And how can we combine this information? How do we work with all this information? That's with GIS. And GIS gives you the opportunity to put all your places where you have been and what you have seen on a map. You can put the DEM, the digital elevation models, or the topography you can put on the map. You can put your measurements, you can put fractures, you can put anything on the map, and you can make also nice cross sections. And by the help of this GIS system, you can slowly build your image of what's really happening. And the funny thing is, it's free. Everybody can download this program and make own maps. You have to learn a bit, but there are very nice tutorials on the internet, and you can learn yourself using this wonderful system. And that system is called QGIS. And I think the next step is the floor to Robert, and he will explain something about what's the system we use of geophysics and how do we use it to understand the subsurface.
Hey, Michel.
Yeah.
Right, so to get a better understanding of our geology, we do geophysics surveying. And what that basically does is we're measuring the ground's electrical properties. So in this slide you can see here we're checking the resistivity of specific or individual rock types and sediment types. So the way that we do that is by using this piece of equipment here, the Volterra, and we use 4 electrodes. So what that does is the 2 outer electrodes will inject current into either the rock or the ground, and the 2 inner electrodes will then measure its potential or voltage, which will then give you your resistivity. And once we have that, we can apply our factor, which will then give us our apparent resistivity, which we will then use for our longer ERT surveys, which I'll go into in a bit. So in the first picture, you can see we're doing a assessment of the sediment type, which is fully dried. In the second picture, we're doing it where it's partially saturated, so you can sort of see the difference between saturation and dry. And then in the third pick of the same sediment type, we're doing fully saturated. And what we noticed was, because the water chemistry that was flowing through there, each time we were going from dry to semi-saturated to fully saturated, it had an effect where it was lowering the resistivity of the sediment. We also did this on, so this is a dike at Ball Alley, which is almost everyone have seen. It's quite visible. We did this here, and it also gave different resistivities. So that way we can use that in our further ERT surveys, and we can basically create like a key for different resistivities to pinpoint to which sort of rock type or sediment type it is. Also, in the fourth picture, I have to make clear that the instrument, it connects via Bluetooth to your phone. That way you can get your measurements and get your results. And so here we are doing an ERT survey. So this is a much larger instrument. We managed to procure this through the Cloud Browse project. And what we can do is have, so instead of 4 electrodes, this is 81 electrodes. And the maximum length we can do is 400 meters. So it consists of 4 cables, 100 meters each. And similar principle to earlier, where you inject your outer electrodes with your current, and your 2 inner electrodes will measure your potential. Here you'll have a different combination of your 2 electrodes, which will measure your potential. So therefore, you get a greater number of data points. And so when you have a larger data point, you can then create your model. So as I said earlier, the max length we can do is 400 meters at a time, which would then give us an exploration depth of 1/6, which is roughly 65 to 70 meters. So here we did a longer survey, and as you can see, we have our different resistivities within. And this is where it links to the Volterra area, where we can get that individual specific rock type or sediment type. And what resistivity we manage to get from there, we can then pinpoint it to what it gives us here. Just to give you an idea of the size of the survey we do, comparison to the island. So this was a survey here, and yeah, this is 300 meters still above sea level, so we still have 300 meters below, but it does give indications at subsurface levels or shallow levels. And yeah, for the next slide, I shall hand you back to my colleague, Michel.
Okay, thank you, Robert. Robert explained very well. So we measure the resistivity of the rocks, and we also measure them at a small scale, so we can find whether this is basalt or andesite, etc. That's what we are going to try. And he said that is also true. We only are very, very shallow according to the whole rock mass we have. So that's also the handicap. So I will lead you through how we work with the geophysics. How do we do an interpretation? So we have this GIS map and all our information on the map. Then we have the map of Ian Baker, and we can see the different layers. And we have, in our GIS system, we can have our lines, our ERT lines, and see where they are exactly according to the geology and all the other information we have. An interesting thing is that Ian Baker, when he came back, he did his PhD as a geologist. When he came back, he found out that here there was a big slip, so here there was a huge landslide that formed Sandy Bay, and here he found out there was also a huge landslide that cuts really into the geology, into the landscape. But it is also an old one, so it was also partly overridden by new volcanic outflows. And I put just this this line I put on the map that you can do with the GIS system, and I see that that line crosses also our measurements here, so that's good to know. And here you have some schematic. Here are the airport boreholes. You have here the slip. This amount of land is just slipped into the ocean. So why are we going to measure here? Because here we have information. We have the airport boreholes. There is sometimes even a description of the airport boreholes, but we can measure the depth, we can measure the chemistry, and well, borehole 5 is active, so we can even do pumping tests on that one. So that gives a lot of more extra information. So then you put, that's how we work. You make a topographical profile, you put in the boreholes and the information in the boreholes. So where was the water strike and where was the static water level? Because the funny thing of this location is that when you drill up to 80, 90 meters, you hit the water and the water rises because it's under pressure. And that's what we call artesian wells. So this is where the water strike was, and this is where the water will rise when you hit that layer into your borehole. Then we do our measurement, and when you combine then the borehole information, also the water level and the water strike, and also the fact that you have this slip here, the slip line, which you can see here, then it makes sense. And also because we measured the resistivities of the rocks, we know that this is a big fault system, this is the slip, and here it's filled with andesitic outflows with a very low resistivity, what we also see because of the blue colors. So by combining all this information, you know that when you drill here, you can find water. When you drill here, you will not find water anymore, and the water is of a very poor quality. So it's always important to start with this kind of measurements and observations before you drill a hole. It's of course, when you have this picture and you don't have those boreholes, then you could ask yourself, will I drill here or shall I drill here? So with new boreholes and doing ERTs, it's important to do more than one borehole, observation boreholes, in order to find the right spot according to the difference you see. And we could really relate our small measurements, rock resistivities, towards the resistivities of the different rock types we find in the bigger picture. Another example is Fisher's Valley. We did it, it's more complicated, but we have a lot of information here. We have boreholes, we have a borehole that cuts into a impermeable layer and loses all the water, and we have active boreholes, and again we see that that slip line is somewhere around. And this is an overview picture of Ben. He made this, and you can see that this area is a marsh area, that's a very wet area, and the water is just coming to the surface. Then again we make this profile, we collate all the different measurements we do, and we look at the geology, and this is the picture we get. And that's quite an interesting picture, because when you only see this, what I say, where are you going to drill? Are you going to drill here, or here, or here? But we did this here because we already have those boreholes, and then we can learn and make this and use this information at other locations for new boreholes. So when you look here, this is a projection from borehole which at the side here. This area has water. In this area there's clay from above, and that's really the wetland. And here's an inflow borehole, here change. So there's water coming here, then you have a change, and then again another change. So you can make an interpretation then, because here we know that this borehole is artesian. We know that in the wetland there's a lot of water coming up. There's also in small boreholes you see the water coming out, and then you find some phenomena here, end of the muddy riverbed, and we find the inflow borehole. So here you really need a combination of existing information in order to understand what's really happening, to make your interpretation. We also looked at similar islands, like that's what Elizabeth also showed, but there is not much resistivity measurements done on islands like St Helena. But we found one example. Actually, I know those guys. That is with a helicopter. They use a different system. They use EM signals in order to measure rock resistivity. And the thing is, they find the same resistivity range as we measure also at St Helena. And they also find the same results by saying, okay, what you measure with the ERT system, you measure rock resistivity, and you don't measure really whether there's water or no water. So you have to use everything in order to understand where you can find the water. So you measure rock types and weathering types, but the water itself you don't see, and you have to use other information in order to understand where the water goes from. And with this sort of systems, you can go up to 200 and 300, even 400 meters of depth and measuring the resistivity of the rocks. And what I found is that one side of the island is completely weathered and has very low resistivities, more like clays, and on the other side of the island you have very high resistivities and almost no weathered rock. And you have a lot of structural changes, and these are the structural changes we are looking for with our system on St Helena in order to find the superficial groundwater. So then, coming back to that geological map and to this sketch, what we learned is that, and that's also what Elizabeth said and also what Ben, is we have a very complex system. We have fractures, we have dikes can be impermeable, we have side dikes, we have rivers that cuts into all the layers, we have moments in between outflows that you get erosion, and somewhere there you have several layers where you have the water. So it's a very complex hydrogeology, and only by using what I said, other information, it will give you insight in what's happening. And this is an interesting picture, because here you see Friars Valley, and here is this thermal infrared photo, and you can see that we really blew it up. You can see that it's really dark here, and it's spreading out. And here you don't see it, Lemon Valley, you don't have that dark spot, so you can maybe say there's not that much water flowing into the ocean. And when we look at Friars Valley, that catchment has a lot of water. It's one of the catchments that has most of the recharge. I think it's ranked,
Yes.
ranked one or two.
It's the top ranking.
Even the top ranking.
For recharge between 500 meters and 690 meters.
Yeah. So this is really combining this with that will give you a lot of information, and that most of the water is just disappearing. So, and then by using geophysics and all the information you can get, you can maybe find where in that valley the water is disappearing. So that's how we try to work it out and combine information. Yeah, and then there's another interesting project, because a lot of scientists use that's called data sonification, and it means that you try to translate your data into music. And when you have long-term, maybe temperature measurements or any kind of measurements, then you want to see the changes, and you can look at the changes by doing mathematical analysis, but you can also hear the changes. And what we did as an experiment, we put an ERT measurement into this program, and we make music out of it. And I don't know, I think we make music out of it, but it's completely silent. He's a witch.
Press it to stop it.
Yeah. So this is an ERT measurement in Fisher's Valley, and it's going from 70 meters up to the top, and it goes all those layers, and every layer has a certain resistivity, and we take that piece of resistivity and we put a tone to it, and then you get this, you get music. It's amazing. I can listen for hours to this. Yeah. Well, this is, of course, a funny way to use data sonification, but the way I use it, for instance, is you have solar wind and you have lightning that strikes into our planet, and that's a very heavy, a very powerful source of a low frequency AM signal, and with a special antenna you can catch up that system and you can sonificate it, and then you hear very funny things in that sonification, and that's the funny thing, it's rhythmic, it's harmonic. So we think that, well, he has a violin, so we are going to make a combination of this music and the violin of Ben. And I think this was a nice end of the slideshow. Yeah, this is also interesting. It's very dangerous to do geophysics. Sometimes you don't even see it. Only when you look afterwards at your picture. Because, look, it's just there, and once it will fall. And we didn't see it. We were working there hammering electrodes. And he was just even standing below it. So we were very lucky. So, any questions?
When's the album coming out?
Yeah, that's takes some time. Yeah. So yeah, it's complex. I think that's clear. But when you want to do a borehole here in this island, first do a geophysical measurement, and then think, okay, maybe this is the spot or that's the spot, and try to find the best spot by taking everything in account. And be also aware that just one drilling may not be the best location. Yeah. And Ben has said that I have to shut up now because it's getting late. I can talk forever, I think, but okay, I shut up now. And no questions, it's also easy then. Okay.